Okay, so thank you, Martin. As you said, I will talk about a project we made under the ICAR Recording Devices Subcommittee about computerized solutions for periodic checking of electronic milk meters. So, as it was a cooperative work, I would like to acknowledge also the co-workers, Martin Burke, Marlena Trinderup from Denmark, Steven Sievert from the USA, and Eric Schilling from the Netherlands. My presentation is linked to the previous one, so I will try not to repeat too many things. First, a few words about the context. We know that in the main countries producing milk, at least European and North American countries, 2 to 25% of the farms are equipped with electronic milk meters. And this number is still increasing, as you can see on the graph. So these are data from France, but it gives you an idea. We have an exponential increase of automatic milking systems and a linear increase of milking parlors equipped with milk meters. So as these, if these milk meters are used for milk performance recording, they have to be checked once a year, as Stephen already said. And this milk meter control is very labor intensive and quite expensive, especially when you have a very big milking parlor, as it's the case in the US. I put a picture here to show you in what it is consisting, gathering milk or water in a bucket and weighing this bucket on a scale. So when you have to do this on, I don't know, maybe 50 milk meters and 3 times on each milk meter, you can imagine how difficult it can be. So there was an urgent need of simplification and of modernization of these practices. And one of them is the use of statistical validation. So this is a possible way of simplification by using continuous data from produced by the electronic milk meters and applied smart statistical methods to determine if the meter is faulty or not. So you have a picture explaining you. The idea would be to switch from the manual checking we are doing currently to monitoring checking here by using data and applying algorithm to determine if the meter is faulty or not. So these have a lot of potential benefits, like replacing the water test, of course, or supplement it. Also to do continuous monitoring, because today we are only doing a control once a year, but we could apply a continuous monitoring that would be much better. Another possibility with the new data exchange technologies and data storage possibilities is to do remote control, gather data from outside of the farm and then determine if the meter is faulty. So to go on this, we decided under the ICAR Recording Devices Subcommittee to make a project called DataCal for data calibration, with the first objective to update the ICAR guidelines to provide standardized statistical models for validating accuracy of EMMs, with the goal to encourage manufacturers or ICAR members to implement them in their software and use them on the field. So Stephen explained that it was partly the case in the US, but in Europe it's not at all the case for the moment. The main milestones of that project were first to review the existing models or methods, then test them on farms, all of them on the same farms, if necessary refine the parameters and update the guidelines with the best models. 5 models or methods were reviewed in the literature or given by manufacturers or also the one applied in the US. They are all based on very different principles. Most of them were developed for several milking stands installation, and only one of them for automatic milking systems. The matter is that only one of these methods is currently used on the field. This is the one presented by Stephen just before, but all other were never tested on more farms than the one used for the papers on which we found them. So I will quickly explain the principles of the methods or models that we decided to keep in our guidelines. The first one, I will go quickly because it was already explained by Stephen. It is the use of expected milk yield from the cow to determine if there is deviation. So comparison between the measured yield and the expected yield from one cow, and then from 1 meter, sum the cow deviations in comparison with the expected yields. Another one is the use of dynamic linear model developed by De Mol and André in Wageningen, where here the principle is to compare the average milk yield produced in one stand with the overall average milk yield on all stands. And then the deviation will be for one stand and one milking station will be a factor from the overall average yield produced on that milking station. If the meter is working properly, then this deviation factor will be null. Another model, the last one for the several milking stand installation, is the use of a lactation model developed by Trinderup from Agrotech. So here, the idea is to explain the observed yield by several variables like the cow identification, the date of milking, the days in milk, and so on. And as this model is quite powerful, by using the residual of the model, we can determine if the meter is faulty or not, in comparison of the residuals of all other meters. For automatic milking systems, the principle is quite simple. We only compare, you can see this in the picture here, the milk yield measured by the robot, the meter from the robot, and sent to the tank. Now on the automatic milking systems, we know exactly the milk destination, so it's easy to compare the milk sent to the tank with the collected milk. There is a more complex method developed by De Mol and André and using a dynamic linear model, but it did not give more information, so we decided to keep a very simple one. So then we tested these methods, models on farms. So we used 2 experimental farms in France, one from the INRA, which was 28 stands rotary. On that farm, we decided to have 3 meters voluntarily out of calibration for 10 days to see if the models were able to detect these deviations. The automatic milking system farm was a farm from the agriculture chamber from Loire-Atlantique. And in that farm, so it was a 1-box robot, we registered very precisely the collection time, date, time, and volume to compare this with the robot. And on both farms, each milk meter was manually checked to get an idea of its real deviation value. So to do that, you have a picture here. We gathered milk on from 5 cows and calculated the difference between what was in the bucket and what was measured by the milk meter. So a few results from that study. You here are on the graph. The different methods, the expected yield method, the lactation model, dynamic linear model, and the deviation that we calculated with these different methods. The black diamonds here are the measured deviation, what we could consider as a reference. You can see that this meter was correct. For all the models, the deviations were still inside the acceptance limits, plus or minus 3%. So this was a correct milk meter. The second one was a faulty milk meter. It was naturally faulty. We did not change anything on that one. You can see that at the beginning of the study here, all the models or methods detected it as underestimating the production. This was confirmed here by the manual checking. Unfortunately, this meter was broken during the study, explaining what we don't have any more data here, and then it was fixed and calibrated by a technician. This was detected by 2 of the models. Only 1 did not detect immediately the changes of calibration. The third example is an example of a meter on which we changed the calibration value. So here we add 5% on the internal calibration value, so the meter was supposed to overestimate by 5% the production. And only one method here, the expected yield method used in the US, detected that deviation. But actually, it was more to see if the methods were sensitive, because we are not looking for to detect such punctual deviations. We made then correlations between measured and estimated deviations. I'm not sure it's easy to see something here, but we see that there is a positive correlation. Here you have the value between measured deviations and the different methods. They are almost the same. There are some slight differences between the models, but in general, we always obtain the same results, and all the models gave us the good deviating meters. But what is important to say is that a reason why there is not a better correlation is that the reference that we used, and which is already used on the field, is not a golden standard, because we only measure the deviation on 5, or actually it's 3 cows, and we did it on 5. Because of the variability of the meter, the deviation value that we have is not an absolute value, but only an idea of this deviation. Actually, it was efficient enough to detect deviating meters, and if we use that kind of method continuously, it will give us furthermore accuracy for detecting those meters. So for the robot farm, you can see here the deviation from collected milk. So here the meter was quite okay, confirmed by the measured deviation, and by the end of April, it started to overestimate the production for an undetermined reason. So it was confirmed again by the manual checking. And then the meter was fixed only 2 months later. Our method detected immediately the fixing, but by applying that kind of model, we could have detected this deviation 2 months earlier than when the technician came on the farm. So what we observed is that all presented models gave quite results to detect deviating meters. We also validated them on private farms for both robots and milking parlors. So that was made in France, but also in Denmark. All the models gave quite good results, but the expected yield and the collected yield methods, as they are very simple to implement, could be easily applied on the field in the near future. I will not detail all the requirements and limitations, because Steven already talked about this, about reliable co-ID, about missing values, etc. Something that I could say about the limitation is that for the moment we don't have solution for robots with more than 1 box, because as we are comparing to the collected milk, it will only give us, if we have 2 or 3 boxes, an idea of the overall deviation, but not the individual deviation of each robot. So from this, we updated the guidelines. Martin presented this morning in the General Assembly. We add a new section called Computerized Solution for Periodic Checking. And I will not detail all this new section. You will find all the details of the calculations and so on into these guidelines. But the general statements are that if the computerized methods are applied as outlined, they can replace the annual routine test. We also recommend to use and to perform this test more frequently than once a year. It is quite easy to do it continuously and at least before each milk recording visit. Another thing important is that this method has to be used for routine tests only and not for the installation tests. And of course, other methods and procedures than the presented one can be subjected by manufacturers or by software suppliers, but they must be approved by ICAR. So to conclude, these statistical methods, we think, will be useful tools to monitor EMM accuracy in the near future in supplement of the field controls. They will not replace the field controls, of course. They must be deployed on the field as soon as possible to allow and to maintain an efficient quality control, because if such methods are not used in the near future, milk recording organizations or dealers will not be able to check the meters on the field. And finally, we do encourage manufacturers and milk recording organizations to implement these methods, in their next herd management software or advice softwares. Thank you for your attention.